We're going over what should be our last project, which is evolutionary game theory. And I actually think this is a great way to end out the course. So what is evolutionary game theory? Well, I know within the project PDF, they talked a lot about the prisoner's dilemma game. But I kind of want to give you guys a different story in order to better understand what evolutionary game theory actually looks at. And so let's imagine we have a little plate full of agar, and we're going to put a little drop of bacteria on that plate in order to watch the bacterial colony grow. Well, that bacterial colony is going to grow, and it's going to keep growing in order to consume all that agar around it. But eventually, the size of the colony is going to reach a point where the food is no longer able to sustain its massive size. So that bacterial colony is going to start to die off and shrink in size. And it's going to shrink in size again until another point where that food constraint no longer becomes an issue, so it can grow in size again. And so we're going to see this cycle of growth and decay over and over and over. And that's essentially what evolutionary game theory looks at. We're going to look at how populations deal with each other and with their limited resources. And from that, we can actually visualize these cool patterns that come out of this competition. And so within this project, we're going to be modifying the prisoner's dilemma game and this idea of population growth and decay in order to create a bit of a simpler game for us to look at. And so within our game, we're going to have two types of players. We're going to have players with the letter C, which are known as cooperators, and we're going to have players with the letter D, which are known as defectors. And so in each round of the game, a given player is going to compete in 9 mini-matches. So it's going to play with all 8 neighbors around it, and then it's going to play a 9th match against itself. And in these mini-matches, there's going to be a scoring system. So in a C versus C match, both players are going to get a score of 1. In a C versus D match, the D player is going to get a score of B, and for most parts of this project, we're going to assume the letter B to have a value greater than 1, and then the C player is going to get 0. So once again, for a C versus D match, the D player gets a score of B, and the C player gets a score of 0. And then finally, in a D versus D match, both players are going to get 0. So let's actually calculate the score for this center player against its 8 neighbors, and then in that final 9th match against itself. So as you can see here, let's start off with this little mini-match. It's a C versus C match, so both players get 1 point each. And then we have another C versus C match. So now this player scores now 2. Then he gets 3. Then he gets 4. Then he gets 5. Then he gets 6. Then he gets 7. Oh, but in this match, this D player is going to get a score of B, and the C player is going to get a score of 0. So we're still going to be at a score of 7 after this match, and then it's going to play its 9th match against itself, where it's going to receive a score of 1. So this C player, in all 9 of its matches, is going to get a total score of 8. And so this seems simple enough, right? The rules are pretty simple, and each player is just going to play 9 mini-matches against all its 8 neighbors, and then 1 round against itself. But you guys should be thinking, let's look at the game board a little bit more. How is this player going to have 9 matches? It looks like it only has 1, 2, 3, 4, 5 neighbors, and then only a total of 6 matches if we include that match against itself. And so that becomes an issue, right? We want to make sure it's fair. We want to make sure that every single player within our game board actually plays 9 matches. So what we're going to end up doing is we're going to do something called wrapping the game board. So we're going to pretend that these edge players actually can see players who are on the opposite edge from them. So as you can see here, this lower edge is going to be able to see the edge opposite to them. So they're going to be able to see these players. And then this edge group is going to be able to see the opposite edge. So it's going to be able to see these players. And this corner player is going to be able to see the opposite corner. So it's going to be able to see this player. And so from this idea of wrapping, we're actually going to be able to make sure that every single player on the board has 9 neighbors to actually do these mini-matches with. And so I think they might have given you this example in class, but what we're going to end up doing is we're going to be creating something called a torus. So if you imagine the sheet of paper here as our game board, remember, each edge is going to be able to see the opposite edge. So this bottom edge of the game board will be able to see this top edge. So what we're doing in reality is we're actually wrapping the game board like this to create a cylinder shape. And then if we remember again, these edge players can see these edge players. So this edge is actually going to wrap again. And we're going to create this donut shape, which is, again, known as a torus. And so by doing this idea of wrapping and copying up all these edges around the original game board, we're actually able to make sure, hey, look, this player now has 9 neighbors. So we're going to take our original game board full of our different defectors and cooperators, and we're going to wrap it. So once again, this edge gets copied over here. This edge gets copied over here. This edge gets copied up here. This edge gets copied down here. And then we're going to copy opposite corners. So the D goes up to here, the C goes down to here, and etc. And so good. Now we have all players having 9 neighbors to fight against. And then we're just going to follow the simple rules that we outlined here. We're going to score each player. So it's pretty easy for these guys in the center, right? Because they have all 9 players. But once again, we run into an issue. How are we going to score these edge players? As you can see here, I've clearly given them a score, but again, they don't have 9 neighbors. Well, since these guys have copied their copied values from the original game board, we're essentially going to give them the same value as that inner player actually got. So, for example, this player is D, and he got a score of 8B. Well, we know we copied this D to be up in this corner, so we're just going to give him the same score. So since this guy has a score of 8B, we're just going to say this guy also has a score of 8B. So even though he doesn't have 9 neighbors, we can still figure out his score. And so again, we're going to do that for all other players. Since, let's go with this guy was copied over here, and since this guy got a score of 8, we're going to copy this guy also to have a score of 8. So good, now we're able to score. And so now the final thing, remember, we're working with evolutionary game theory. We want to see how, according to like these constraints of population, how population actually changes over time. So what we're going to do is we're going to update our board. And so how do we actually end up updating? Well, for each player within the inner board, that player is going to look at all 9 of its neighbors. So it's going to look at all 8 of its neighbors, and then it's going to look at itself, and it's going to see who has the highest score. And then whoever has that highest score, that inner player is going to end up taking that player's role. So, for example, let's look at this player, who's originally a C. He's going to look at all the neighbors around him and himself. And he's going to realize, oh, this guy has the highest score. And he's going to say, okay, I'm going to take on this guy's role. So what role did he actually end up having? He had a role of D. And so this player, since he sees a score of 8B, which is the highest score, and that player had a role of D, now he's going to become a D. And that actually makes sense, right, according to evolution. If we see other organisms being more successful than ourselves, we're going to try and take on their characteristics in order to make ourselves more successful within the wild. And so we're going to do that for every single player. Every single player is going to look at its 9 neighbors, and it's going to say, oh, who has the highest score? I'm going to take on their characteristics. So for like this guy, again, he sees, oh, look, that guy has a score of 8B. What kind of type player was he? Well, he was a type D player, so then I'm also going to be D. And so then we update the matrix, right? And now we see all our new players, and a lot of them have switched to D because they noticed, oh, this D was successful within the last round. And so we're essentially going to be repeating these steps over and over and over. We're going to take our board, we're going to wrap it, we're going to score it, and then we're going to update it. And we're going to do this for a certain number of generations. And we're going to visualize what the board looks like at every single generation. And what you're going to end up seeing is that these cool patterns actually arise. And so that's all this week's project is. What you're going to be doing is you're going to be creating a game board of size n by n for this matrix. You're going to have to figure out how to write a function in order to wrap this game board. So you're going to have to figure out how to copy this edge of the matrix over here, this edge of the matrix up here, and etc. And so that's really going to rely on your knowledge of matrix concatenation. And then after that, we're going to figure out how to score it. So you're going to be writing another function. You're going to figure out how to get a player to look at all of its 8 neighbors and then play these simple rules. And so you're going to figure out how to score this board. And then finally, you're going to write a function in order to update the board. And this entire time, we're going to be visualizing, again, just to see those cool patterns that are going to end up arising. So this project is simultaneously easy and hard, right? It's easy because we have easy rules that we're working with, right? This isn't too complex to work with. But it's going to be a little bit confusing, right? We have to figure out how to access neighbors and how to score these neighbors and do these mini matches. That's just going to be a little bit of a thought process, but it shouldn't be anything too bad. So I hope this video helped, and I won't see you guys in the next one because this is the final video lecture of the course. I hope you guys have a good one.